And so I'm going to basically set the ground rules and facilitate, but I'm not going to do much talking except to set up the problem set. Rob Hovsapian is going to talk to us about the nature of cyber physical systems and some of the challenges associated with that. Rob's got a substantial background. I've known him since days at Florida State, Idaho National Lab, and now he's at National Renewable Energy Lab doing thoughtful things with energy, and I think you'll find his talk impressing. Charles Forsberg just showed up on video, so he's was a very senior person at Oak Ridge National Lab. We've sparred on things quite a bit over the years, and now he's a professor in nuclear science and engineering at MIT, and we still continue to collaborate. He's going to talk about some of the challenges of timing and what that means for energy storage, short and long term. And then Sarah Davis is going to wrap up with the real challenges, which have to do with the human side of things, policy, hesitancy, changing mindsets, and so forth. Sarah has been around the energy and resilience domain, especially in terms of working with communities and helping them to find their way forward and go through growing pains that inevitably come with change. And so what we'll do then is wrap up the panel with some Q&A. Let me see if I can show our screen here. So let me start out the conversation and set the stage for our panel. We all know that our energy system is transforming, and we're going to go from burning dirty old fossil fuels, coal, and even natural gas to a clean world where we buy billions or trillions of dollars worth of PV panels and batteries from China, and we put them out in the sun, and we have power at least part of the day and maybe some of the night. So we're headed in that direction. Everybody knows that's simple. Actually, that going in that direction works okay as an incremental solution. So we're using more sustainable sources. We're thinking more thoughtfully about the value proposition of energy, getting away from levelized cost of electricity as sort of the be all end all in terms of value. And we've got advanced technologies that enable us to have a more resilient and reliable system. And so we see implementation of DERs, microgrids, and we even see market reform in terms of, for example, grid services, timing markets, and so forth. So the challenge now is to look at the big picture. So we've used fossil fuels as our go-to source for energy in large part during the Industrial Revolution. But we say that we're going to switch over to intermittent renewables. So PV and wind are available when they're available, and they're providing something like 4.5% of our power right now. So they're displacing that much fossil fuel, presumably. But now we're going to multiply that by some 20 times, that penetration of intermittent renewables. What will that do to our balance of energy at any given time? And then thirdly, if you look at utilization, we've had cheaply available energy for a long time. And so we're willing to live with a situation that we reject 2 times as much energy as we use. And so that doesn't bother us. We just pump more oil or dig more coal. But now when we have to capture energy from the wild, from the sun and wind, and we have to convert it and move it and so forth, it matters. Efficiency matters. So we're going to have to deal with this potential change in mindset that we need to get greater utilization of our energy sources. So that just sort of sets the stage for the real speakers. So I want to pass off to Rob Hovsapian next, who's going to talk about cyber physical transformation. Thanks.
Good afternoon, everybody. I'm just going to give a quick overview of the development of next generation cyber physical characterization platform. Next slide, Paul. So the topic I'm going to talk about, why do we need this characterization environment, and what is the application of the machine learning for increased power grid resiliency? And then talk a little bit about the NREL's advanced research on integrated energy systems infrastructure that allows us to do some of that, and give a couple use cases of how do we leverage those environment and infrastructure. Next slide. So why do we need the characterization environment? As utilities operate and own most of the cyber physical systems in the nation. And if you look at those, the graph over there to the left of it, is most of the cyber physical systems are inside the firewalls, and which so far they served us right. But as our power systems changing, and we're relying more and more into the integrating with the outside systems, whether they're IoT devices, weather information, or emergency signals, that we're more and more relying on cyber physical systems that are outside of the firewall. So how do we bring in this together, and how do we, in order for us to better understand those assets and how are they connected, it will require for us to provide a system to reduce the risk of this integration between those systems that are outside of the firewalls and the inside of the firewalls. And how do we create that? Next slide. So some of the system, what you see on top there is the kind of system that most utilities have today. They have IT systems, data operations, were mostly used for smart metering, billing systems, data archiving, and also there's tools out there for the development for operations. And now more and more we're seeing a machine learning operations data, which is being used in order to better understand how those systems get integrated, utilizing the actual data that the utilities have. But what's the new, and it's looking at the simulation ops, which is how, in order for us to better understand how the grid will react with the future operation systems and the future devices, it requires us to better understand that. So creating that simulation ops environment, this is the digital twin of the system that allows us to come up with ways to integrate both the development environment and better ways of articulating the machine learning and utilizing the machine learning techniques in that simulation ops. That's where it will require a lot more, not only digital twinning, but also hardware in the loop and power hardware in the loop of the systems. Next slide can give us a little bit more of how. So if we look at, if you hit one more return, Paul. A couple more. Sorry, I didn't mean to have the animation in there. Yeah, thank you. So in this case, everything to the left of the dotted red line is where we are today. I mean, we have the IT and the data ops system that utilities do a very good job in load forecasting, looking at restoration plan and asset risk management, and also to the some development work that's happening, and more we're seeing the machine learning ops and the simulation. So far, it has been looking at it from the non-dynamic perspective, but more and more it will, for us to look at the dynamic aspect of it, the dynamic recovery, black start, power quality type challenges. It will require more of a real-time simulation platform in order to be able to understand not only this from a power system perspective, but also from the communication perspective. So tying the controls, the communication, and the power systems together in that dynamic environment. And that from the real-time hardware perspective and also from the machine learning perspective is start giving us a better environment in order to be able to articulate and see how those systems interact with each other. And if we look at the outside of the power system side, I mean, for example, Amazon and Google X and Project X, they're kind of looking at the same things as well. I mean, if you look at from the Amazons and Googles, they look at it from, they're doing more of a targeted advertisement. That's what they're good at. But now they're looking at it, can we do more targeted forecasting for energy and energy load forecasting, for example? So you're seeing more and more Googles and Amazons are getting into that machine learning ops and the simulation ops side of the things, not necessarily from the power system quality side, but more so from the how to do that targeting, on better understanding the customer participation side of it into the system. So that's the new growth area of the machine learning and more of the real-time simulation ops side of it. Next slide. And if we look at the lab scales today, it's, for example, at many of the academic and the small labs is they have a fixed data, they're limited on the data and the volume of the data that we use, but they have very large, rich algorithms, and that they test the various kind of the algorithms and how do they interact in those limited data sets. If you look at the large system on the right side, where you look at from a utility side, they're rich in data and they have actual live data that's being collected in real time, but it's very limited and fixed in the algorithms that do it, which gives an opportunity is how do we bring those two, mix them together? If you go to the next slide, Paul. So this allows us to go ahead and create that real-time simulation environment that ties both the rich algorithm from the laboratories and academics and scientists, and tying it to rich data side of it from the utilities, and looking at those rich data with the various algorithm in actual hardware and power hardware in the loop type setting, in order to better understand those interaction of those devices together. And in order to achieve that, so what requires for us to do is, next slide, please, creating the environment that allows us to do both from the power system side in real, as mentioned, in real-time tools, whether it's various vendors with RTDS, Opal, Typhoon. You can look at it from a power system real-time emulation side, but also looking on the lower right side, it will require ability to do controls at the speed of the 100 to 200 nanosecond in order to be able to understand how those controllers are interacting with the power system at a 50 microsecond time step on the top right and on the bottom right from the controllers. But what's becoming more and more important is looking at the communication layer and running at a speed of the communication in order to be able to understand the communication between the power system, the advanced control, and the communication at the speed of the communication. That's an area where it's becoming more imperative for us to have that. It's creating an emulation for the communication is no longer, it will address a steady state solutions, but if we want to look at from a real-time real-time dynamic events, it will becomes important for us to have that communication at a speed of the communication interacted with both the controller as well as the power system device side. And then it also becomes important to how do you tie that from a high performance computing, looking at the cases where you can run it faster than real time in order to predict events before you use your real time hardware in the loop or power hardware in the loop. And I have an example that we'll talk about that later on. That's our team here at NREL is working on. Next slide. So this is the communication environment that we're developing. We're looking at the digital real-time simulations, whether those are Opal RT, Typhoon, or RTDS, is tying it to actual hardware, which is shown on the right side. So those are the devices, the IoT devices, the distribution automation devices, the AMIs, the micro PMUs. So those are the devices and how they're interacting with each other at the 10,000 levels of actual controller hardware in the loop of those devices. And in the middle is the layer that allows the broker that all the communication that emulates the actual real world environment, whether they're uh, distribution level or a sub-transmission to distribution level type connections or a community campus level type analysis. It allows us to do those kind of what if scenarios with those, both from the power system side on the left on the RTDS, but also from the communication side using the actual controller hardwares in a 10,000 thousands to 10,000 device levels. Next slide. So in order for us to understand that, it becomes important to look at the not only I mean, historically, what we've done is we did a controller hardware in the loop of actual either power converters or IoT or um, uh, power converters or micro PMUs or PMUs, and how do they interact. But more and more, we're seeing the importance of the IoT type technologies, whether they're electrical vehicle or a weather information or emergency signals that's being broadcast. And so it becomes more and more important to understand those IoT integration with the digital real-time simulation of the power system, and how do we tie those together with the rest of the operation, and more importantly, bringing the human side of it as well, and consumers part of that decision making. How do we integrate that human in the loop aspects of it as well? Next slide. So to do that at NREL, what we're doing is we're developing this advanced research energy systems interface, and we're addressing three main challenges. One of it is we're seeing, Paul talked about the changes that we're seeing in power systems, and we're seeing more and more various sides of systems that are interacting with each other. Historically, it was transmission to distribution and load, but now we're seeing more of a kilowatt system talking to megawatt system, and megawatt system talking to the gigawatt power plants. So those various physical sides of the systems that are interaction with each other, and we're seeing large number of the controllers that are they're communicating. Before, where we had 20, 30 devices talking to each other, that was a large interaction. But now more and more we're seeing with electrical vehicle, with the PV rooftop solars, and so we're seeing more and more devices, and in the millions and 10 millions of those interaction. So for us to understand that interaction of those large number of the devices. And the third thing is we have started also seeing multiple diverse technologies that traditionally they have not communicated with each other. IoT of the emergency weather, to talking to your aggregator, or talking to your utilities. I mean, those are becoming diverse technologies that previously have not worked together. So I'm trying to understand those interaction of those. So in order to do that, we're creating this virtual emulation environment that allows us to tie those various technologies together to address that. Next slide. So what we're creating as part of the Aries is what you see in the middle is that virtual emulation environment, or the digital real-time simulation environment. It has a mix of the large cluster of digital real-time simulation, have about 14 to 15 RTDS systems, 5 to 6 Typhoon units, and 4 or 5 Opal RTs that are all clustered together in this 25 cluster nodes of digital real-time simulation that are trying to emulate those large campus type system, regional type analysis systems. And in order, and not only from a modeling perspective, but looking at the left side, it also gives us the circle, the yellow circle there, that actual hardware, whether they're renewable wind or PV panels, power PV inverters. We have a battery, 1 megawatt, 1 megawatt hour battery that allows us to look at that interaction. We're also looking at it from the machine learning side, a thermal emulator that we develop that allowing us to look at and emulate various sizes, the scalability of the size of the thermal emulator. So that could be a coal power plant or a nuclear power plant at various sizes, and how does it interact with the rest of the digital twin of the system. Or actually, we're working with our colleagues, and in this case, Clay's still on with Cordova Electric, is looking at can we stream real world data from the hydro side and look at that hydro to be part of the digital twin in the system. So it gives us both hydro from a bulk power, thermal, as well as the renewable energy in this large mix of the digital real-time simulation environment. And also we have a controllable grid interface that takes a 20 megawatt power from the utilities and allows us to vary that at various conditions to see various impacts, whether it's a voltage variation or a frequency variation, and see how the test articles under the test will behave under those various conditions. Next slide. One more. Sorry, I should have took those animations out, Paul. One more. So one of the important part is looking at it is the benefits and the things that we're missing, and it's important for us to start including that is the communication side of it. We're doing a good job with the controller emulation, controller hardware in the loop at the various lab, various academia. We're doing very good job with looking at the large power systems, But tying all these things together with the communication layer at the speed of the communication, and how do those things interact under various these dynamic conditions, whether it's a black star or cyber black stars, of how do they interact to it, is becoming the important aspects of the why we're creating those environments, so developing this. Next slide. This is one of the use cases we're looking at it, where the cascading outages, where we run the power system with the communication in real time. So this allows us to calibrate and see what's the setting for the relay setting on the real time side, but also faster than real time, we run it in a high performance computing, various kind of event or scenarios, and see as those events or failures happen, what kind of cascading fault or we will see in the system, and allows us to calibrate the protection system based on the setting. So this kind of shows the value of both the real-time simulation, the communication, as well as faster than real time with high performance computing, and tying all those three systems together. It's becoming more and more important for us to do those tightly integrated real-time high performance with the communication together, as seen in these use cases. The next slide, please. And in these next cases, we're showing where, looking at the various power system that has the interaction of those power devices together, but coming and tying on top of it is the AMI data. One of the projects that we're doing that was presented earlier, that we're looking at how would the AMI information allows us to do segmentation or islanding of the system. How do we look at the sensor data in order to make a decision whether is the system stable for the AMI to do the islanding of the system, tying that to the weather data, tying it to the forecasting data and the human interactions with it. So all those are becoming more and more important to, not only from the power system side, but look at all those external systems that, and how do they interact on top of each other. I believe that's my next last slide. Next, Paul. This is the team. I mean, there's I'm just presenting it here, but there's also a group of team at NRELs working with us. I'm going to acknowledge Mayang, Cheyenne, Manish. They're all part of the team here that are deeply into this setting up this environment at NREL. I'll yield for any questions now or after the rest of the talks.
It looks like we've got a couple questions. Rob, there's a question for you in chat. Are there white papers or NREL reports on this research? You're on mute as well.
There's ARIS's website that describes some of those systems, and any other information, please feel free to contact me, or the ARIS's website also has a email and a phone number for communication team that can support that. And there was another question from Alex about the SEEP. We are tightly integrated with SEEP. SEEP does the communication side of the cyber analysis, and on the it is part of ARIS. And what I was showing on my slide is the actual running the communication at the speed of those communication in the system that we have. So it works hand to hand with SIP. SIP does the simulation side, and we do the actual running of those communication protocols in the system itself.
So while Charles is dialing in, I have another question for you, Rob. You really emphasize the communication side of this, and I think that's important. I wonder about often the ability to emulate real world conditions. So one thing that I wonder about is I see more and more discussion about cybersecurity and access control and so forth. So, integrated system M&S that they're working on.
Yeah, actually, the question that Alex has was important also. And I should have mentioned it in my presentation. In the SEEP environment that our cyber team looks at it from the vulnerability perspective of those communications, whether it's a wireless or various protocols. The setup that we're doing as part of ARIS based on the actual communication, we're looking at using the actual protocols itself. So when we're setting up the simulation environment that looks at the controller talking to the power system devices, whether it's a power hardware in the loop or a controller hardware in the loop, its connectivity is actual protocol itself. So whether it's a Modbus or DMP3 or 61850, we'll use the same protocols. Also,
this is Charles Forsberg.
Charles, you may have to turn off your speakers on your, yeah, there you go.
Yes, I should be in place.
Yep, okay. All right, Rob, were you just finishing up a question or answer?
yeah, and so we're looking at it from actual protocols itself, and also we're working with our colleagues from a 5G perspective and a wireless perspective as well, and be able to run those protocols. So we're actually running the protocols itself rather than the emulation of the protocols. So it's our colleagues at SEEP, they look at it from the vulnerability of those protocols and how to protect ourselves. We look at it from actually running the protocol itself in this hardware environment and to see what vulnerability or issue we'll find with it.
Neat. Okay, thanks, Rob. Charles, I think you're on. Are you going to be able to share your screen?
Yes.
Great.
I'm going to discuss a slightly different problem. The million gigawatt hour heat storage challenge. I have the next slide. This is sort of a summary, and then we'll go into the details. There are two perspectives on moving to a low carbon energy system. First one is the challenge is producing low carbon energy. Second one is the challenge is delivering low carbon energy to the customer when needed. And these are very radically different challenges. The difference is storage to enable delivery of energy when needed. Now, historically, the US requires about 6 weeks of energy storage. That's based on experience. If you have less than that, bad things happen. That works out to 3.4 million gigawatt hours, which implies that we actually have a multi-million gigawatt hour storage challenge, which leads to the general conclusion is that energy resilience is all about stored energy. If you don't have stored energy, you're going to freeze in the dark. I have the next slide. So it's not a low carbon energy challenge, it's a low carbon energy storage challenge. I have the next slide. This shows the existing energy storage in the US energy system. And of course, storage is required to meet variable energy demand and unplanned events. Typically in nuclear reactors, we have 9 to 12 months of energy storage. In oil, we have about a 90-day inventory. Natural gas, we have about 30 days, plus what's in pipelines and some dual fuel customers. And in coal, we have 110 days. People didn't buy that storage because they like storage. They bought it because otherwise, bad things happened. In contrast, we discussed going to solar PV and wind, but they have zero storage. So I have the next slide. Now, it turns out that wind and solar had two challenges. The first one is generation does not match demand on a daily to yearly basis. On the left, we show what happens if California is 50% wind and solar. There's not much wind in California. The solar is in gold. The demand, of course, goes up and down on a daily basis. And what you note here is that production does not match when demand occurs. There are times of surplus energy and demand when there's shortage. On the right, we show the solar flux over 1 year at noon versus latitude. We're at the mid-latitudes, and what that implies is that the solar output, the solar panel can collect, is less than half as much in January as it is in June. However, the peak energy demand in the United States actually occurs in January because of heating, not in June. A totally out of sync system. We have the next slide. Now, batteries are not a solution to a million gigawatt hour energy storage challenge. On the right, we show the price of utility batteries, the entire systems over the last several years, and battery cost is leveling out around $500 per kilowatt hour installed. Given a million gigawatt hours, that's a $500 trillion for a million gigawatt hours of storage. We have a gross national product of the United States that's $22 billion, In short, the battery solution would cost 20 times the US GNP. But now let's turn to look to pump storage, the historical primary storage mechanism used in the electrical grid on the next slide. Pump storage is not a solution either if you have a 1,000,000 gigawatt-hour storage challenge. If we're going to get 1,000,000 gigawatt-hours, we're going to have to increase pumped hydro by 1,800 times. And this begins to get into the questions is, are there enough mountains in the United States, or do we need another Rocky Mountains to boost our capacity? That, let us turn to the next slide and begin to look at what might be, look at the electrification. And again, it's not a solution, but for somewhat different reasons. Central problem is the electrical grid separates energy production and most of the storage from the customer. And 40% of the cost of delivered energy, of electricity, which is the transmission system and the distribution system shown in green and brown, is sized to meet peak energy demand. And what that means is electricity is a really bad solution to meet peak energy demands, because if you're going to meet peak demand for 100 hours a year, that sizes the grid and determines a large fraction of the total cost of electricity. Now, that's not a challenge with oil and gas, because they do not have this bottleneck before the customer site. We have the next slide. Now, the low-cost energy system, what it means is storage can cost more than energy. With fossil fuels, energy is expensive, storage is cheap. We never valued the price of storage. What that implies is we need a low-carbon fossil fuel equivalent for affordable stored energy. And there are three options. The first option is hydrocarbon liquid fuels, nuclear biofuels to replace oil. The second option are gaseous fuels, hydrogen to replace natural gas. And the third is electricity with heat storage. These are options where there are economic methods to store 1,000,000 gigawatt hours of heat at a cost that is substantially less than the gross national product of the United States. I have the next slide. Here we show that real resistance it requires multiple energy carriers. We're talking about 3 energy carriers that will be the rest of this discussion: hydrocarbon liquids, gaseous fuels, and electricity. In red is the storage costs, and what of course you note here is hydrocarbon fuels are cheap to store, followed by natural gas. Electricity prices, of course, are very high. Now, let's take a look at each of these carriers. The next slide, I'd like to start the discussion with gaseous fuels with storage. To make the observation, I would like to discuss the second gas transition. Next slide. Now, if you were around in London in 1807, you'd have found the big headline of the year. The most impressive headline of the year is the marvelous new gas lighting system that was being installed in London. Remember, this is 1807, over 200 years ago. We've used gaseous fuels for over 2 centuries, and the reasons why is they're easy and cheap to store, and they're easy and cheap to deliver. How we use them. Now, what's interesting is the history of gaseous fuels. It's a history of hydrogen fuels. Initially, the gaseous fuel was town gas, carbon monoxide, and hydrogen from coal. Then in the 1950s, somebody came along with this newfangled stuff called natural gas. We started a conversion. That was mostly completed by the 1960s in the United States, but it was the mid-70s before that occurred in Great Britain. So the question is, should we start a second transition, a transition using hydrogen? May I have the next slide? Now, there are multiple low-carbon hydrogen production options. The obvious one is steam reforming of natural gas with sequestration of carbon dioxide. That's clearly the near-term option based on existing technology, and it's relatively economic if you have the combination of low-priced natural gas and good sequestration sites. Texas, Ohio, Pennsylvania. The other option that gets a lot of discussion is electrolysis of water. On the right, we show the cost of hydrogen versus the capacity factor of the electrolysis plant. Turns out electrolysis plants are really, really, really expensive. Very high capital cost. And that strongly favors nuclear plants with high capacity factors. You're operating 80–90% of the time. In contrast, solar hydrogen is very, very expensive. We would, of course, use the same storage and distribution system. So I have the next slide. Take a look at hydrocarbon liquid fuels with storage. What we need here is a different feedstock for a low-carbon hydrocarbon liquid fuels production. Drive the next slide. Take a look at how we produce liquid fuels today. That is the existing fossil fuel system to produce liquid hydrocarbon fuels and feedstocks. Now, we start out with something called crude oil. For those who are not familiar with it, crude oil has a widely varying chemical composition. In terms of viscosity, you have something that is lighter than acetone or water, to viscous crude oils at room temperature that have the consistency of peanut butter. Take all that stuff, shove it through this complicated chemical plant, and out comes gasoline, diesel, jet fuel, and chemical feedstocks. Important point, the starting material is inhomogeneous and it's a mess. Next slide. We have an option. We can switch feedstocks from crude oil to biomass carbon, eliminates adding carbon dioxide to the atmosphere. Start with biomass, a mixture of materials containing carbon, hydrogen, and oxygen. We send it to a nuclear biorefinery system. And if you could just hit the click button one more time, some other stuff will show up. We add massive quantities of heat and hydrogen to produce liquid hydrocarbon fuels that go to the atmosphere. Now, the next slide shows what is required for a large-scale biofuel system. And this is my one chemistry slide, but it's an essential chemicals slide. Today, if you look at biofuels, liquid hydrocarbon biofuels, we start with biomass. We add a lot of oxygen, produce hydrocarbon fuels and carbon dioxide. And the carbon is used for multiple purposes. First, of course, we have to have carbon in the final product, the gasoline, diesel, and jet fuel. Second, we use carbon oxidation to remove the oxygen from the biofuels and provide energy to run the process. Our alternative, nuclear biomass system, where we start with biomass plus hydrogen plus nuclear heat to produce hydrocarbons and water. When we do this, we have external hydrogen and heat that doubles the energy. Okay, I'll go back over this slide because it's the central chemistry slide. The bottom line is that with a traditional biomass fuel, we start with biomass, we add oxygen, we get hydrocarbon fuels and carbon dioxide. Now, the carbon's used for a bunch of reasons. Of course, we have to have carbon in the final feedstock, the hydrocarbon fuels, and we use carbon oxidation to remove oxygen from the hydrocarbon, and we also use it to provide energy for the process. The alternative is the nuclear biofuels option. We take biomass, add mega quantities of hydrogen, nuclear heat to produce hydrocarbons and water. And when you do this, the external hydrogen to heat doubles the energy of the hydrocarbon fuels per unit of feedstock. And what it also does is enables the use of low carbon, low energy value, high carbon content biomass feedstocks. And it changes a situation from where biomass is a limitation to where we have abundant biomass to meet the requirements. Next slide. Next slide. And again, initial studies indicate both nationally and globally sufficient biomass to replace all oil with a nuclear biofuel system without major impacts on food and fiber prices. Now, it's very important when you read the literature to realize people think about biomass as an energy source, so all of the literature is written in that context. And when you think in that context, you say, boy, we got a problem. In this case, we're thinking of it more of a chemical engineering perspective. That is, carbon is a carbon source, not necessarily an energy source. However, the option does require massive nuclear heat and hydrogen if we're going to globally replace all oil within the biomass system. I have the next slide. Now let's take a quick look at electricity with heat storage. This is about replacing stocks of coal, oil, natural gas used to produce electricity. Of course, we maintain nuclear as a stored heat form. I have the next slide. Heat storage in the electric grid couples to heat sources. We have our nuclear heat source or concentrated solar power source on the left. Red, in the red box, we take a cold fluid like nitrate salt, heat it up, and put it into a hot fluid tank, primarily as nitrate salt or other fluids. If we have low-priced electricity, we take the cold salt, heat it up electrically, and put it into the hot tank. On the right, in yellow, we have the power block. As we need variable power, we take hot fluid, provide the heat to the power block, which may have an output many times that of the nuclear reactor, and return cold fluid to the tank. Storage separates heat generation source from the power block. Do I have the next slide? I'm showing an example here of thermal storage in concentrated solar power plants. Capital cost goals that you need to make these systems really work well are somewhere around $20 per kilowatt hour of heat storage. Batteries, of course, are over $500 a kilowatt hour heat storage. Two-tank nitrate systems shown at the right used in solar power plants are $60 to $70 per kilowatt hour. But there's some advanced thermal storage methods using crushed rock that are expected to lower that cost to $10 per kilowatt hour electric. In short, heat storage has the potential to meet the required cost goals to use it at the million gigawatt hour scale. I have the next slide, which I think is also probably the last slide. And the basic conclusion is very simple. Resilience is energy storage. Storage, not energy production, is the low carbon challenge. We require millions, I repeat, millions of gigawatt hours storage. And once you recognize that, you have only 4 storage options at scale: hydrocarbon biofuels, heat storage, hydrogen, and nuclear fuels. All of the other contenders simply are not affordable in the context of a gross national product that is only $22 trillion. Thank you very much.
I'd like to get Sarah Davis on the line here and talk to us a little about the real world issues and how we address them.
Thank you, Paul. Good afternoon, everyone. I hope that you can see my screen. As Paul mentioned, I will be digging into another challenge, this one more on the people side of things, as we look to where we're going to build these new resources out. My name is Sarah Davis, and I'm the founder and CEO of SRD Consulting. We're a land use planning firm based in the Denver, Colorado metro, and we're focused on decarbonizing both our transportation and energy systems. I also volunteer as an advisor to the DOE-funded Solar at Scale initiative, which is being supported by the International City and County Managers Association and the American Planning Association to develop guidelines for how to build out larger solar farms across the United States. I also spend some time co-chairing the micromobility subgroup of the Colorado Electric Vehicle Coalition, as my practice focuses both on renewable energy, including battery storage, as well as electric vehicle adoption. I won't go into too much detail on my agenda, but at a high level, today I'm going to be focusing the first half of my presentation on looking at land use planning as energy planning, and kind of cutting down from the regional planning that we do at the utility level down to the community and individual household level on how to ensure energy resilience. The second half of my presentation will reflect on how to foster better public participation and to spur grassroots efforts in building out more resilient energy systems. As many of my panelists have reflected on, our energy landscape has changed greatly in the United States over the last 200 years. I look back even further at kind of pre-industrial revolution timeframe, when we were very much tied to where our energy resources and usage was coming from. Much of the Midwest, especially the northern Midwest, was used for timber and forestry that was then used in individual homes to heat and to also cook with. We also saw throughout the Midwest and our farming communities the harnessing of wind energy for pumping water used for irrigation and such. We shifted around the turn of the century to more of a centralized energy system as we looked to increase not only the amount of energy output, but also the different types of fuel sources that we were using, both domestically and internationally. We looked at a more concentrated system where we relied heavily on transmission and distribution systems to support load. And this shifted greatly not only who bore the brunt of living within the immediacy of these generating facilities, but also, the changing technologies that came along with the introduction of nuclear power, as well as an expansion of coal and natural gas-fired power plants. Today, we're seeing a modernization occur within our nation's electricity system as we move away from that centralized system and look at ways that we can decentralize and have a more distributed energy system. As the other panelists looked at, this comes with a lot of other complications, including that cybersecurity piece, as well as what makes sense from a scalability standpoint in terms of where to add things like stationary storage to our grid, and how to make all of the Internet of Things and electric vehicles and everything else that we're looking to electrify communicate with each other, so that the system is more dynamic and able to fluctuate as either individual events or longstanding drains on the system impact our grid availability. I use this slide just to kind of remind ourselves that the energy system is but part of a larger system within not only our urban, but suburban and rural areas. And as we continue to invest in these developments, we have to think of ways that we can not only leverage those investments, but also maximize them and how they interact with others. So coming up with solutions on both sides of the equation, reducing energy demand through energy efficiency, coming up with creative ways to spread things around like heat that's generated through energy generation, and then how to continue to not only ensure that our energy system is sustainable, but that it's resilient, that we're able to bounce back from acute events, as well as longer term risks to our system. As an urban planner and someone who works in community, I see this play out in a lot of different ways, but at the end of the day, this resilient energy transition, it's important to note that it's different than a sustainable energy transition. Resiliency focuses much more on bouncing back from those immediate, acute, isolated incidents, which are being felt throughout the country in a lot of different ways, shapes, and forms. And so that impacts what those local solutions are going to be. In the desert Southwest, it's going to look very different than parts of northern Minnesota that can get to -40 degrees. But at the end of the day, it's integrating our regional and local energy planning, as well as development, so that we can leverage all of the funds, whether federal or private investment, to maximize the impacts of those facilities. And then a focus on critical loads. And so, we have to identify what is truly critical to ensuring, our ability to live. In some areas of this country, that is ensuring heating. For all of us, that's ensuring an ability to store and to heat food, to have available water that is drinkable. We need a sense of system redundancy so that if there is a threat, whether a natural disaster or a man-made threat to our energy system, that there is a redundant backup available to help support those critical loads. All of this helps to ensure that our grid is more flexible, and a sense or a level of ability to operate while the grid is down. So that may mean backing up specific buildings, areas of town. The image on this slide just is a high-level image of a Main Street microgrid, where certain emergency services, places that people could gather if they needed shelter, would be able to be powered in the event that the larger energy system was down through isolation devices that island that Main Street area. Now, there's a lot of things that are driving energy policy in the country today, but I would say climate change and natural disasters are at the forefront of a lot of people's minds. We're starting to see them impact more and more people, businesses, and our ability to do everything from transport goods to being able to provide services. And this is something that we're seeing not only for different energy policy, but also different and new technologies within the energy sector. There's also a desire to better manage our resources. This can be something that's very locally felt, but also regionally, and not only at the state level, also federally. What are the trade-offs to ensuring highest and best use of the lands that we have, and how can we best manage the resources locally through employing the right technologies at the right time. And then finally, a big driver is our local and regional businesses, whether they've committed through their ESG or other kind of value system goals, as well as individuals, people that are really looking at their system locally, at their own home, and how they can ensure resiliency in the face of whatever the future brings. And I think, one of the things we have to start in this whole conversation doing a better job of leveraging those existing community resources that we already have. So as we look at the city level, the neighborhood level, however you define community, we have a series of resources, whether those are physical, more ethereal in terms of knowledge and skills, and also institutions that are available, many of which you all represent and are connecting at this conference about. And so I really implore you to think of ways to continue to funnel that down to communities, to staff, and even our nonprofit organizations who are working to make these things actually happen on the ground. We need all the modeling we can get in order to prove that these technologies are possible to solve a lot of the challenges that our country is facing. But at the end of the day, the rubber does hit the road somewhere. And so, maximizing what we already have in place, whether that's communication systems, institutional knowledge, skills and experiences, as well as, existing fuels and things like that, can go a long way to helping us get on that road. Now, a lot of the solutions that my panelists have mentioned are, they have to get built somewhere. And so thinking about these as place-based solutions, what makes sense based on geography, based on the people who live there, based on what industries are in and around a specific area is really key to making sure that the right technologies are being applied. So when we think of microgrids, it's less of a technology challenge and becomes more of a policy challenge. And so, we have to start peeling those layers back and figuring out, where are the gaps and how can we all work together, work with our regional utilities in order to come up with paths forward that make the most sense. There's also the individual household level. Each one of us has a home in which we live, and focusing on energy efficiency is huge. I think heat pumps and even improved insulation in homes goes a long way to reducing our individual demand, which then can reduce those home critical loads. I think putting them on their own separate critical load panel that could then be backfed by, some form of on-site solar and a storage component can go a long way to ensuring resiliency. And if we're resilient at the individual household level, it improves resiliency at that community level, where things are a little bit more complicated from a policy standpoint. I would add that there are other aspects of resiliency. As Rob mentioned, communications is a key part of that. And we have to think about ways that all of these interface and can be better leveraged so that our invested dollars go as far as they can. One of the communities I was working in had a communications challenge. They were a mountain community. There was only really one part of town where you could get reliable cell phone service. And so during emergencies, that was a hot commodity. And so looking at, potentially backing up a building in town where food was available with a communications tower enhancement, was a solution that we explored as a way to improve not only energy reliability, but also that communications piece. Similar stories can be said about water. Potable water is a key resource, especially in our rural communities. And then coming up with creative solutions. I think we are all watching how electric vehicles are becoming a dynamic part of our power system as we explore things like vehicle to grid or vehicle to home solutions. A creative solution that came up in one of the projects I was working on was this idea of neighborhood hubs, where in more dispersed communities, maybe there were one or two homes that were identified as a neighborhood hub, and a lot would go into ensuring a backup of power to allow for sheltering during adverse events. And that kind of puts more resiliency in the heart of communities instead of having it be a very kind of separated community center type solution. Now I'm going to talk a little bit more about how to foster that public participation piece that's so key to getting these facilities built. As an urban planner, we talk a lot about how to ensure, quote, meaningful participation. And I think it's something that's often aspired to and very rarely defined. Over the next couple of slides, I'll be talking about something called community power, which in a conference like this can be taken a lot of different ways, but I'm talking about it in this context in terms of empowering our residents and our community members to make change and to get involved in the public process. We in this country believe in democracy, and I think oftentimes we see that play out as this photo illustrates as a community meeting, as a forum, a caucus, a place where people can come together and share ideas. But as our society continues to change, we have to come up with creative ways to ensure that we aren't leaving people out of these discussions, and that we are empowering people who are residents of our communities to not only take part in the larger discussion that's happening, but also the decision-making process. And one big way to do that is through participatory budgeting at the city level primarily, but bringing people into the process of making decisions about where dollars are spent and where staff time is being spent. And I would make the argument that this is in a way to spur additional investment and more development of these resilient and sustainable energy systems. Informing people about projects is not enough. Notifying someone in the paper that something's happening, it just isn't enough. We have to start talking about these critical energy systems more deliberately and more all-encompassing in everything that we're doing. So whether it's housing or new light rail projects, energy has got to be a key part of the conversation, and we've got to bring everybody up to a level of knowledge so that they can make a meaningful participation and make a meaningful contribution through that participation. This quote, "Change moves as fast as trust," is from a good friend of mine, Lashita Sayer. And I think it really rings true, especially as we look to communities who dealt with environmental justice challenges around some of our other aging energy infrastructure. We have to look really honestly at where we've failed in the past. We can't begin to repair and move forward if we aren't able to reflect on where things just didn't go well. You'll hear from people who have residential solar on their roofs And over the course of the year since they had their system installed, the programs changed and they're no longer able to sell back to the grid, or the cost at which they are is a fraction of what they had originally kind of bought in on. These all go to fracture trust, which is key if we're going to move forward in any way, shape, or form, especially with something that's as intimate as our energy system. In the United States, we're very used to just being able to turn on a light switch and trust that the light is going to come on, that our computer is going to turn on, that our cell phone is going to be charged when we wake up, and pretty soon that our car is going to be as well. And we have to recognize that not everyone has felt that security. And even if they have, they might not be aware of how fragile our system is. I actually woke up this morning. I live in just outside of Denver in Xcel Energy's territory, and my power was out. And I didn't have an ETA on when it was going to be back on. Luckily, it was by this afternoon, or otherwise my internet wouldn't have been working either. So, it's critical to not only business moving forward, but at-home medical devices functioning, our food storage being able to sustain for days and weeks, and everything that we do. So building trust with community really focuses on breaking down barriers that have historically existed within our participatory government process. One way to do that is to identify cultural brokers within your communities, people who come from the subset of your community that you're trying to reach, who can broker that conversation and bring people into the fold, but also identify new and creative ways to get people involved. Hopefully it's not just Zoom meetings like this, but we've seen a lot of people let their guard down when you have an open house of someone who has installed a heat pump and a battery at their home, to really see that this is something that's possible. And if this person can do it, maybe that's something that I could look at too. We see that really make waves in the EV adoption. If you can get someone behind the wheel of an EV, they're much more likely to consider it when they go to buy their next car. I think a lot of that goes to building trust and showing people there is no behind the curtain. We're being as upfront about this technology, its limitations, and its potential as we can be. And then, of course, co-designing with the community, whatever process you're trying to do. We're seeing a change in who's getting involved and how they're choosing to get involved in public process. And I think we have to recognize that this next generation of residents in our communities, they have grown up in front of a computer on a screen, and we have to figure out ways to leverage that technology effectively and interestingly. So overall, it's removing barriers to participation, not just making it fun and exciting, but also making sure that you're drawing the connections between the work you're doing and people's lives. Why does it matter? Why do we need a resilient energy system, and why does that impact all of us on a day-to-day basis? Making sure that you're holding meetings and that you're including public participation in ways that removes any kind of hostility as we look to expand renewable energy projects. One of the limiting factors, NREL just came out with some data around this, one of the limiting factors for renewable energy proliferation in this country is local attitudes. Communities that are straight out adopting moratoriums against large-scale solar and wind are cutting away at all of the land availability that we once thought was going to be our savior in terms of energy transition. So focusing on quality over quantity, we don't want to have people participate to death, but rather make meaningful connections to their lives and to this important work that we're all doing. So I'll end on a case study. This is a community that I worked with. Gold Hill is about 30 minutes outside of Boulder, Colorado. And to no surprise to many of you, is full of some amazing, well-educated citizens who really wanted to push the envelope. They're an unincorporated community designated federally as a rural dispersed mountain town that's about 300 residents, and they have been on the front lines of the fires and the floods here in Colorado, and so it's very personal to them. Lack of water availability and the need to have propane generated backup for their homes because they have these adverse events more frequently. They had one even while we were doing the planning for this feasibility study. If you're interested, resilientgoldhill.com, you can find a copy of this report, but we basically looked at, what's possible from a technology standpoint, with resiliency leading kind of the charge, with renewable energy and low carbon being kind of the secondary goal. And we looked at both the community scale, Main Street microgrids, community center with backup and things like that, as well as individual household level. And so I encourage all of you as homeowners or even renters to explore the report. It includes some great, very current cost assessments on different solutions that you can employ in your home and that we can be looking at the community level. So finally, just some takeaways. Land use planning at the beginning and end of it is energy planning. Where our buildings go, how they conform to the surrounding fabric of our cities and our suburban and rural neighborhoods it is part of the energy equation. And as we focus on a just transition to resilient energy systems, we have to make sure that we're looking both at the community and individual household level. Historically, we plan regionally, and we've got to start integrating that regional energy planning with our local communities and making sure that we're all talking to each other and figuring out what's the best, where that rubber hits the road. And then, of course, as we look to engage the community, make sure that we're including education so that we can focus on, not only spurring investment and development, but making sure that our communities are coming along with us for those solutions and not going to be an impediment down the road. And with that, I'll take any questions. Thank you so much.
Okay, thanks. Thanks, Sarah. There is one question already in the chat, and I think James Graham raises a good point. That's questioning whether it's realistic that all these people are going to be involved in the conversation. What percentage of the population can make a meaningful contribution on these technical issues? And I would, Sarah, you might want to address that, and James, I'd invite you to come off mute if you like to follow up on that question.
I'll start by answering it. I think that's a really great question, and it's something that other planners in my position really grapple with because all of our communities largely act as their own individual kingdoms, right? Every city, township has a mayor, a city manager, and then city staff, and they do a lot of different things. And especially the more rural areas are pretty understaffed in terms of dealing with really technical issues. And so my hope is that we do start having more education, more of kind of a trickle down from all of the work that you all are doing to our communities to arm them with the truth. Unfortunately, I've been in a lot of public meetings where people grab the latest headlines of a battery or even a nuclear facility that has had some kind of incident and uses that as a way to undermine this transition. And so the more people that we can bring along, I think the more robust that conversation can be. At the end of the day, what I'm seeing is a lot of either uninformed, underinformed, or misinformed people being quite outspoken against new projects and facilities that are being proposed. And while nuclear facilities, as an example, are approved federally, things like solar, wind, and even stationary storage are approved locally. And you know, there is opportunity for people to come out against in very vocal ways. So it's hard to put a percentage on it. I think today it's a very small percent, but I'm hopeful as we start to kind of meld these ideas together and we see that there's potential optimization and overlap, that we'll see more and more.
Thanks,
Thanks, Sarah, for that informed answer. I'm glad to think that you, in fact, have thought about this, and it certainly is a challenge.
Definitely. Well, in the middle of my energy career, I took a brief hiatus and worked writing zoning code. And I did the rewrite of Albany's zoning code. And it's a very technical process as well. And we had to be really thoughtful about what parts of it we brought to community. And I think that's the same to be said for our energy system. You know, there are certain things that it just doesn't make sense to gauge kind of the general consensus on, but when people are coming out and against things like new transmission line siting, which is going to have a big impact on where future energy generation is sited, that's where I think we have to start to kind of educate people on, you know, why and how did this turn out to look the way that it does.
Yeah, and I think, you know, you brought up the issue that we really need place-based solutions. So the solution in our town in Montana probably is different from a solution where my parents grew up in Ohio, and, you know, Florida has different needs. I might interject, one of the things that I've researched a little bit lately, partnering with my wife, who's an artist educator, we've looked at some of the human aspects of resilience, and we tried to find, you know, what's the link between the individuals and the small groups and communities, because there aren't many people who sort of talk about a model that ties those together. And what we found is, one, that hope, agency, and meaning are key aspects of this integrative model. If people have hope and they have some sense that they can make a difference, and there's some shared meaning out there that people develop as they interact, then you're much better postured to sense, anticipate, you know, respond and adapt to things in a constructive way. And so one thing I've been watching for over the last, year and a half now, is what is the impact of all of the COVID response on these resilient mechanisms? Because in our community, there are a lot of people who view cultural activities like music, public art, markets, and so forth as very important contributors to building a shared sense of meaning, reinforcing those networks of people, and even informing that chart that Sarah, you showed, that had all these resources, and somebody knows how to sew, and somebody knows how to, you know, fix electrical power systems and so forth. If you don't have that social fabric, and even sort of exercising the social fabric in the context of something to reflect and really build some shared meaning for the community, then it's hard to come to some sort of a consensus on, you know, do we put a nuclear reactor in the town? Do we have giant salt storage caverns or tanks? And those end up being showstoppers, as you've basically pointed out. Charles and Rob, I wonder if you want to chime in on either of these.
Well, I think the issue is going to be, at the end of the day, how do you make sure the lights stay on and the houses stay heated? You know, people will have debates that go on forever, but it's amazing how blackouts suddenly get people's attention. Now, sometimes it's a little unfortunate what the results are. I mean, California is building gas turbines as fast as GE can send them in by rail, because they are rotating blackouts, and every politician knows that they're about to die if they don't fix the problem. But unfortunately, we have a system right now that tends to only respond when the lights go out or the house gets cold, and hopefully we can fix that, but that's not the direction we're currently heading.
Hey, Paul, my typing is not working. May I ask a question right along the lines of, I actually work as a, a speech coach for two different labs for years and years and years. And it was interesting sometimes to watch even scientists and engineers resist the idea of learning to effectively communicate their science. It's really odd to watch because it's pretty clear if nobody knows what we're doing, what good do we do, and are we going to get funded for doing it? So I've done this so long that I joke I get to change the world one willing scientist at a time. And I have a whole group of people who, kind of avoid me in a lunchroom sometimes. And, I heard a quote say about nuclear power with the French one time was that they taught it early to the kids in elementary school, middle school, those people were educated on exactly how nuclear power works. And and the boogeyman and all the uninformed stuff were taken out of it. They really tried to do it with facts. My question for you is, have you thought of a strategy, a real time, not a pie in the sky, and boy, this sounds good, but how you're going to change the world one person at a time, and what sort of educational methods have you thought about or wanted to implement? I mean, I'm very fascinated by your work, but I'm also understand what you're up against in terms of a misinformed public, a media that loves to see it bleed or burn, and people that just are kind of lazy and like the other gentleman said, until the mayor's mom gets killed at a four-way stop, we're not getting a traffic light. So I'll leave it at that, but that's what I've been thinking about throughout your presentation. I really appreciate it and may send some contact information. Well done.
Sarah, you want to comment?
Thank you. Yeah, I mean, I think that's a really important question. And I think that, looking at individual people, it can get quite cumbersome, right? Everybody's a unique individual, or at least we like to think so. But I think you touched on something that's really important, which is the education piece, and trying to integrate energy education into not only our school systems, but also as adults. We all have to pay a utility bill at the end of the day or at the end of the month. And so, how can we use these touch points to just help bring people along? And I think part of it is dispelling some of those myths. And with nuclear, we have a little bit of a harder message to push, at least here in the United States, because thanks to The Simpsons, we saw nuclear power meltdowns play out on our television screens in a humorous way, but in a way that really stuck in people's minds. And so I think something that we as a society need to start thinking of is how do we make this more tangible for people? How do we, how do we create the next Grey's Anatomy that's focused on people who work in a national energy lab, where, you are challenging these ideas, but doing it in a way where there's also the people side, because we all are people. And I think that sticks, that storytelling is what sticks out in people's minds. I would add to that, as we look to, bring more people into the public process, we have to kind of think about everything that we've done up until this point has kind of left somebody out. When I was in planning school 20 years ago, it was have meetings at different times of the day. You have to catch those working moms. They can't come to a night meeting, and nowadays nobody goes to public meetings. Nobody wants to sit through a public meeting unless they're really angry about something. I would say very rarely do you capture the people that are happy and that they're there just to say, good job, you guys are doing a great job. So I think we have to focus on ways to bring people along. Paul mentioned cultural events. I think that is a great way to connect people to energy. We need it. We need it to power these venues. We need it to, to power the vehicles that we use to get to the venue. And so how can we have an interactive display, or how can we switch out the shuttle bus that we're using to something that's a little bit more revolutionary, that is going to get people there without them even realizing. I think, not to bring in too many cultural references, but I think Disney, back when Walt Disney World opened 50 years ago, really was trying to do that with transportation, and then it kind of stalled out. Autotopia used to be like the coolest ride at Disney World because it was these futuristic looking cars. Well, now they're still gas powered. So take a kid whose parents have an EV. They're like, what is this? It takes forever for the engine to heat up. It takes forever for me to go anywhere. And it smells, and I think those are the types of things where you've gotta make that story be what sticks in people's minds and carry them through.
Thanks to Rob and Charles and Sarah, and to the those of you who've come and shared in this conversation with us. I certainly enjoyed the get together, and I hope that you did, and look forward to any follow-up with either people who are here or somebody that you tell about this event. So thanks, everybody.
Thank you.
Thank you. Enjoy the rest of the conference.
Yeah, thank you to all the presenters and good questions. Just a reminder, tomorrow we got lots more great stuff. We do have a welcome video for Senator Risch, got Dr. Craig Rieger talking, Dr. Ron Fisher, and Dr. David Woods all speaking next or tomorrow. So lots of good stuff, and goes Wednesday and Thursday as well. So appreciate everybody, and thank you for your time. Yeah.
Thanks.
Thank you. Bye-bye.